Hi, Mr. Balogh here, continuing on from part one of the how to integrate over charge. Make sure you watch part one of this video series so that you have context for what it is I'm about to do. What we want to do is we want to find the total charge on this rod here. It's lying along the x-axis. We usually are given some sort of information, and I'm just going to give this to you, that the linear charge density is constant and uniform, okay? I don't know exactly what the numbers are, but we know that since it's constant and uniform, that over the entire length of this rod, right, with total charge on it, right, Q, we should be able to find the total charge. And you're like, "Oh, well, Mr. Bailey, you just told me that the total charge is Q." I know, I know. I want to show you that the method works. All right, and then we'll tweak it just a little bit. So what is it we're looking for? We're looking for the total charge on the rod. How are we going to find it? We're going to find it by adding up all the little contributions of charge that make up the rod. What do I mean by that? Well, what I like to do is I like to draw like a little tiny representative chunk. I just take this little tiny piece that's between those two lines, right? And that's my little DQ. Okay, and what we need to do is we need to get this DQ written in a way that the integral can sink its teeth into it, and you can turn the cranks that you've learned in your calculus classes. But how do we do that? Well, first of all, this little piece of charge does have a distance from the origin, a distance x. And I want that to be a variable. I want that to range all over the charge. I want it to go from 0, where the rod begins, to wherever the rod is ending, right, at its length. So we specify, we pick a little representative piece, and then we define some sort of variable distance that we can try and manipulate here. We're going to use our definition of linear charge density to figure this out. I'm going to rearrange it, okay, and then realize that if I want to find this little chunk of charge, it's not lambda I'm taking a little chunk of. That's constant. That's uniform. That's the same. What I'm taking is a little tiny piece of length. And in the language that we have here, this is just a symbol switch. It's not a meaning switch, right? Our length is lined up along the x-axis. So I can just go ahead and write that as dx. Well, now I know what my dq is, and so I can go ahead and substitute that up into there, right? This is going to be the integral of lambda dx. Now, there aren't any integrals in physics that don't have limits. We never do this indefinite integral plus c business. So we need to give it limits. So it starts at where the rod starts, right? These are the physical parameters of the system. The rod starts on the origin, and it ends at whatever length the rod happens to be. And now I can sink my teeth in here. This is the calculus part, okay? I move my constant out. I'm integrating from 0 to L dx. Well, that's going to be lambda x evaluated from 0 to L, which is lambda times L, which, lo and behold, is the total charge, right? Lambda times L is Q. And again, that should come as no surprise that we got the total charge since we know the total charge. But now let's tweak this just a little bit. And again, if I'm going too fast, feel free to go ahead and pause me, right? Rewind, see it again, that sort of stuff. I know I'm going fast on purpose because you have that pause button. So let's say now that we are told that the linear charge density is non-uniform and varies with the length of the rod. So A is just some number, don't know what it is, don't care. But we can see from this that the charge density of this rod is going to start at 0 at the origin over here, okay, where x equals 0, right? There's going to be no charge. But as we go along the length of the rod and as we get to the end, the charge is going to get really big, right? It's going as x cubed. We want to find the total charge on a rod that has this strange charge distribution on it. Again, we're going to start with what we want to find. We want to find the total charge. We're going to find it by adding up all the little tiny pieces of dq. Nothing changes in the picture up here. I'm still going to use this little dq. I'm still going to use this x. I'm still going to go from 0 to L. And so it shouldn't come as any surprise that we'll write this as lambda dx from 0 to L. Only now we can put in this non-uniform charge density equation, right? And we can go ahead and turn the crank on our integration. It's going to be x to the fourth over 4, evaluated from 0 to L, which is going to be AL to the fourth, all over 4, and that will be in coulombs, right? So there we have it. I was able to find what the total charge is on this rod based on this non-uniform charge density. If I knew what A was and I knew what L was, boom, I'd be able to tell you exactly what the charge on this rod is. The actual, answers we're getting here are not important. It's this process of being able to start with what you want to find, figure out what the little chunk is, get it into terms that the universe, the integral can understand and work in, right? And then finally turning that crank to be able to do it. The entirety of your math 5A, 5B, math 6, all that sort of stuff exists right there. What we're going to be spending most of our time in Physics 4B concentrating on is this beginning portion, right? This setting up of the integral so that you can finally get to a point where you can just do the integral. And I hate to break it to you, but you're going to get to a point where you're going to be begging me to just do integrals. Mr. Balogh, please just tell me the integral to do, and I'll do it. But really, all of the physics is taking place here in the beginning. So buckle up. I've got some more geometries to show you, and then you'll be ready for the next chapter when integration gets thrown in heavy in the context of electric fields. Part 2 is coming up. I want to show you spherical geometries, and then we'll do cylindrical, and then we'll be done with this chapter.